Ecotech Consulting have created an Aspen flowsheet simulation for the Syngas-Methanol-DME process. Selection of thermodynamic models for the Aspen simulation were based on heuristics considering operating conditions, compound properties, energy asymmetries, and model capabilities. For all units operating above 10 bar, the Peng-Robinson-Wong-Sandler model, PRWS for short, was selected. It outperformed alternatives due to its lower VLE pressure prediction error for polar mixtures like methanol, water, and DME, superior performance for high-pressure systems with energy asymmetries, and direct access to binary interaction parameters in Aspen's database, avoiding reliance on external data that could introduce inaccuracies. For the methanol reactor, the Shorzen-Chuber-Renon model, SR for short, was chosen over PRWS, since it's a model widely used in industry for methanol synthesis. Unlike PRWS, SR applies volume translations to correct for inaccuracies in computing liquid molar volume, ensuring precise density and thermodynamic property predictions. For all low-pressure units operating below 10 bar, like distillation columns and the amine sweetening process, the non-random two-liquid model, NRTL for short, was selected. NRTL excels at representing highly non-ideal polar liquid mixtures under low pressures. Its enthalpic accuracy, reliable binary interaction data, and widespread industrial validation makes it favorable compared to shortlisted alternatives.
Unit operation models can influence the accuracy of results. They range from simple to rigorous, and their selection depends on the process requirements and available data. The water-gas shift reactor uses R-stoic as its reaction stoichiometry and conversion are known, enabling precise control over the desired hydrogen to carbon monoxide ratio. The methanol reactor is also modelled by R-stoic. While R-equil could model vapor-liquid equilibrium more rigorously, it requires unavailable inputs that could introduce errors from calculation approximations. This makes R-stoic a more practical choice since conversion is directly specified. The DME reactor uses R-stoic as it does not reach reaction or phase equilibrium, and all necessary inputs are available. Flash 2 is chosen for flash drums due to its compatibility with two output streams. The distillation columns are modelled using DSEW as it is more appropriate and simplified for this preliminary design stage. With light and heavy keys specified along with their recoveries, DSEW computes key parameters using WG calculation methods. For absorption, Step 2 provides an efficient approximation by specifying component recoveries. However, it sacrifices some accuracy and detail since it does not account for any operating conditions, physical designs of the column, or thermodynamic qualities. Overall, the selected models are a compromise between accuracy and practicality, laying the foundation for more detailed simulations later in the process design.
The Syngas-to-DME process is divided into four main sections. In the pre-treatment section, the syngas feedstock undergoes 3 stages of compression with interstage cooling, increasing the pressure to 39 bar and reaching a final temperature of 220 Celsius. The pressurized feedstock is then sent to a water-gas shift reactor where the hydrogen to carbon monoxide ratio is adjusted to 2:1, making it suitable for the methanol synthesis reaction downstream. The reactor effluent enters a flash drum where water condenses and is recycled back to the reactor to maintain a water-to-carbon ratio of 2:1, thereby preventing side reactions. Excess water is purged through stream 6. Returning to the flash drum, the vapor stream passes through an expansion valve before entering the absorption section, where 99% of the CO2 is separated and directed to the CO2 compression section. The remaining crude syngas is then fed to the syngas-to-methanol section. In the CO2 compression section, CO2 is pressurized to 100 bar using a 4-stage compression system with interstage cooling, producing CO2 at a rate of 56.6 thousand tons per year. In the syngas-to-methanol section, on the other hand, crude syngas is pressurized to 75 bar through a 4-stage compression with interstage cooling. It then enters the methanol reactor where an isothermal reaction at 250 Celsius takes place to 90% conversion. The reactor effluent is then routed through a turbine with an expansion valve, reducing the pressure to 75 bar and then to 30 bar, while simultaneously cooling it to 151 Celsius. The cooled effluent flows into the reactor's flash drum, where methanol and a small amount of water are separated into the liquid stream and sent to the methanol-to-DME section, while unreacted crude syngas is recycled back to the reactor with a 30% purge split to avoid accumulation of inerts. Finally, in the methanol-to-DME section, crude methanol is pumped to 39 bar and preheated to 160 Celsius before entering the DME reactor, where 95.1% of the methanol is converted into DME. The reactor effluent at 300 Celsius passes through a turbine to reduce its pressure to 10 bar, after which it's pre-cooled to 50 Celsius. The cooled effluent enters the first distillation column, where nearly all DME is recovered at a purity of 99.9 weight% with a production rate of approximately 19.2 thousand tons per year. The column bottoms is then expanded to 7 bar and enters the second distillation column, where 93% of the methanol is recovered at a 94 weight% purity and recycled back to the DME reactor.
Heat consumption and generation of the different types of units has been analyzed to assess the scope of energy integration, which will focus on heaters and coolers due to their significant energy demands, accounting for 49% of the total heat duties of the process. Reactors, distillation columns, and compressor interstage coolers are excluded from the study to avoid thermodynamic interdependencies that could compromise process control and safety. Following this scope, the streams available for heat integration are 2 cold streams, streams 7 and 24, and 3 hot streams, streams 4, 18, and 27. However, stream 18 is excluded from the pinch analysis due to 2 limitations. Its temperature profile would lead to the violation of the minimum temperature approach with either cold stream, and its physical location in the plant is relatively far from the cold streams. These are the inlet and outlet temperatures of the streams selected for the heat integration, along with their heat duties. However, all 4 streams undergo phase change within their respective temperature ranges, which cannot be reflected in the pinch method due to its assumption of constant heat capacity. To address this, heating and cooling profiles for the streams were generated using Aspen to identify the sensible heat portions before phase change for each stream, leading to the following adjusted outlet temperatures and duties. An interval diagram was produced, using a minimum approach temperature of 15 degrees, which strikes an optimal trade-off between the total heat exchanged and the driving force. With this, the cascade diagram was constructed, revealing that the minimum heating requirement for the sensible heat transfer is 375 kilowatts, while all the sensible cooling requirements can be satisfied. This also implies that operation is above the pinch, since only external heating utilities are required.
The heat exchanger network design is shown here, and the matches were selected according to the expected proximity of the streams in the plant layout. Here is the Aspen final case simulation after implementing the 2 heat exchangers. Note that, while the duties calculated using the pinch method provided a baseline, the actual duties of these exchangers are higher. This is because some of the latent heat from the phase changes can be transferred within the exchangers, while still respecting the minimum temperature approach. The remaining energy requirements of the process are met using high and medium pressure steam as hot utilities, chosen based on the temperature profiles of the streams. Cooling utilities consist of cooling water and steam generation at low and medium pressure, which recovers some of the value from the heat rejected by reactors and compressors, and they were then modeled in Aspen. Implementing this heat exchanger network would result in the total energy consumption being reduced by 16%, which would translate into a cost saving of 310,000 euros per year. The product flow rates and purities are shown in the stream section of the results summary. This process produces 19.4 metric tons per year of DME, with a purity of 99.9%, along with 56.5 metric tons per year of pure carbon dioxide as a byproduct. Despite Aspen displaying some input translation warnings, the simulation successfully converged and ran without any errors or warnings, as shown in the control panel and run status. In conclusion, Ecotech Consulting has successfully designed and simulated a Syngas-to-DME process for Bentham Corporation, achieving high purity outputs and paving the way for greener, safer, and cost-effective solutions.